Yes, we will. So thank you for the organizers for having me. I'm really having a blast, and if any of you have additional questions or thoughts about anything I'll show here, I would love to talk to you this week while I'm here. The title kind of derives from the fact that I'm really interested in thinking about questions in sort of as wildly and radically interdisciplinary ways as possible. And so I'll show one idea of sort of how we analyze specifically fuzzy dark matter halos using one of those ideas. So the bones of the talk are thus. I'll introduce you to what I call ultralight dark matter. You might know it as fuzzy dark matter. We'll talk about calculating the eigenstates of a fuzzy dark matter halo and what that even means. This is sort of the interdisciplinary part. And then we're going to have an interactive bit where you're going to get to choose your own adventure. So either I will tell you about the core halo-mass relation, and I'll quickly introduce what that is so you can decide if you care about it. Or I will tell you about supernova feedback. And this choose your own adventure model I've completely stolen from Caitlin Schutz, so thank you, Caitlin. Apparently you don't remember this talk, but I do. All right, so ultralight dark matter, what is it? This is maybe preaching to the choir here, but nevertheless, I like to start with the idea that lambda CDM is a really good model, right? That's why it survived so long. A lot of these observational results are coming up lambda CDM, and so it tells us something like in a galaxy where we live, here, there is this dark matter halo that lives around the regular matter or the visible matter or the baryons or whatever, right? And so I'm completely discounting any modified gravity or sort of like macho ideas here for the duration of this talk. If you want to fight me on that, come fight me after. However, I put it to you that lambda CDM is not a great model because it doesn't tell me what the dark matter particle is. And so some people say, that's fine, I can put in CDM and then I can do sort of like, baryonic feedback and stuff in the forefront, and that's what I really care about, but I care to know what most of our universe is made up of, and it annoys me. And so I love this Venn diagram from Tim Tate because it sort of shows all of the ideas that have been put out there and sort of like, analyzed and explored in different levels. And so there's a real diversity of ideas here, but for the purposes of this talk, we will be living in the axion space. And sort of to complement maybe Chanda's talk yesterday to convince you that, axions rule and WIMPs drool, this is the popularity of axion abstracts at the very least APS meetings that has been going up recently, and that sort of is confirmed by trends in like snowmass and P5 and such. So ultralight dark matter, what is it? Also known as fuzzy dark matter. So it is an axion-like scalar boson. For the cases that I consider in this talk, the mass is sort of on the order of 10 to the minus 22 eV, which means that its de Broglie wavelength is on the order of a kiloparsec. So that means that these Bose-Einstein condensate effects become really visible on the size of the galaxy, and this is why I find it interesting, because I think it's really, really cool phenomenology. Historically, it came about because people started being interested in sort of solving these small-scale problems, such as the core cusp problem over here, with something like dark matter rather than baryonic feedback. I'm not saying whether it is or isn't a problem, but that is sort of historically why it came about. But really, I'm just using this as an excuse to tell you about sort of what the two bits of a fuzzy dark matter halo that I want you to keep in mind. So here in this extremely expertly drawn diagram, what we have in the gray is sort of what, a CDM sort of cuspy profile might look like. And we see that the ULDM profile in black sort of really matches on the outsides. I call this the skirt of the ULDM or fuzzy dark matter halo. And then in the center, we have this core. This is the Bose-Einstein condensate that we really like. This is also referred to sometimes as a soliton. And so that's, where the popularity in solving the small scale crisis comes from. And to thank for this, we have this set of equations known as the Schrödinger-Poisson system. There are other names that you could use for it, but that's what I use it. And so what we have here in the first equation is an equation that tells us how psi evolves. So psi is the wave function of dark matter. A little bit more on what that means in a minute, but it's basically telling us that the wave function of dark matter evolves due to some kinetic term and also a coupling with phi, and phi itself is the gravitational potential of the dark matter, which evolves with the familiar Poisson equation, which depends on like a bunch of constants, including the mass of the axion MA and the absolute value of psi squared. So the mass of the axion times psi squared then is just the density of dark matter. So this is the observable that we really want to get to. So, if you've done any simulations of fuzzy dark matter, number one, you have my sympathies, and number two, this is probably the system of equations that you're solving, right? And this system of equations is really, really great because it allows us to calculate a halo's eigenstates using a couple of assumptions. So this is almost the same equation that I just showed you. I've done two little things. One, I've pulled the psi out. That's just math. I can do that. But two, I've put this phi in angular brackets, which is a really small change in notation that's actually carrying a big assumption here. And the assumption is that for a system that I am considering, phi is basically stationary, meaning that it doesn't really evolve in time. It has some profile that oscillates a little bit, but it doesn't oscillate that far from some equilibrium profile on average. And so if I make that assumption, which I'm just asserting now, I'm not showing you proof of that, then I can sort of for the moment forget about the Poisson equation. There's no rho here. And what I have is something that you might have scribbled all over your Quantum 1 notebook somewhere, and this is the time-independent Schrodinger equation. And the reason this is interesting is because I can solve for the eigenstates of this much in the same way that I can solve for the eigenstates of a hydrogen atom. It's really the same procedure, which is to say that I assume separability here. So I assume that there's a radial part of the wave function and then the familiar YLMs. And I can do, as a theorist does, and torture Mathematica into solving that system of equations for me. And I come out with these sort of radial profiles for the eigenstates of some dark matter structure, some fuzzy dark matter structure with a stationary phi, right? And the really interesting one is up here. So n equals 0, L equals 0. So this is the ground state. All of these are assumed to be m equals 0, where these are sort of the quantum numbers that we index things by. So this is the ground state. This is the soliton. This is that core that we really like. And this is what we really wanted to get at because that's one of the observable things. And then the skirt, the outwards of this, is all of these excited states, along with their YLM parts, of course, added together. So it's really a superposition of eigenstates that makes up a halo. And the halo in question might look something like this. So here I'm showing you a formation of a halo that I'm forming by colliding two blobs of dark matter here. And then I get this sort of like really pretty simulation of what a fuzzy dark matter halo looks like. A few things to notice here. So first we have the core here. This is that like central core that we like that solves the Korkas problem, blah, blah, blah. But we also have constructive interference, so these denser, lighter regions, but also destructive interference, so regions that are underdense. And so, some papers have used this to sort of put limits on the mass based on sort of the dynamical heating that you get from this and stuff like that. But those are sort of the two main observables of a ULDM halo. But now, if I take this ULDM halo, for instance, or a halo that I've made in one of my very painful simulations, and then I decompose it into its eigenstates, I can see the exact amount of mass that lives in each of these types of eigenstates. And so that looks a little bit something like this. So here we have absolute value of CL squared, which is to say how much mass of, how much of the dark matter density lives in each of the L states, so summing over the N states, as a function of time. Time here is in code units because I'm a simulator. You can consider this about a Hubble time. And don't look at anything before 0.1 because the halo hasn't formed yet, so this is basically box noise. So what we see here is that for L equals 0, so those are the spherically symmetric states, that is sort of the highest line here. Most of the mass is in those, but it's still only like 30–40%, and it has these like big sort of oscillations. Mind you, the gray here is showing you just what's in the very ground state, so that's n equals 0, L equals 0, m equals 0, so that's that core, that's that soliton that we really like. And then L equals 1 states, we have even less mass, L equals 2, less, et cetera, but all of these together make up that skirt. So what would have been really nice to find that this is sort of like mostly a ground state with some perturbations, because then I could use perturbation theory and really save myself the numerical hassle. Unfortunately, that's not quite true, but we can nevertheless use this approach to sort of say something about the qualitative behavior of our halos. And so just to complete the hydrogen atom parallel here, right, if we're thinking of a hydrogen atom, you might be thinking about a single electron that is orbiting a proton, and it lives in these orbitals that look something like this. In the case of fuzzy dark matter, what you have is a metric bajillion of axions that don't have a central thing that they're orbiting, and they're not held together by E and M, they're held together by gravity, and so what you really need is that ground state, and you can superimpose one of the excited states to see what it does. So here, in recreating this orbital, what we superimpose is an L equals 0 state, so it's the ground state plus any spherically symmetric state, and what you see is that the core breathes, and this is one of the really qualitative effects that we see in all of these simulations. If you superimpose an L equals 1 state, so this is a dipole, what you see is that it moves back and forth. This is very evident in simulations because the center of mass does a random walk around the center, which is very annoying because then you have to chase it around the center. And if you impose a quadrupole, you see a quadrupole. But so that's sort of finishing my, my hydrogen atom parallel. Now, given this sort of slightly wacky way of looking at a dark matter halo as a really, really big hydrogen atom, here are your two options. So this is where you get to choose your own adventure on what you want to hear about. So on the one hand, we have the core halo mass relation. This answers the question of how big is that central core given a ULDM halo, right? That's something that we observationally want to know. And, it'll be important for something like estimating ULDM particle mass per observed core sizes or inferring that these cores are from something like ULDM rather than from the many other things they could be. And so here we really use 3D simulations plus eigenstates. On the other hand, we have a supernova feedback in ULDM Halo's version of the world. This answers the question, how would supernovae affect measurements of particle mass based on the core profile? Feedback is important in CDM halos, so this is sort of our first step towards understanding what it does to ULDM halos. Mind you, these are 1D simulations and sort of less eigenstates than this, really. And if you zoned out through all of that and don't care, this one is slightly longer and this one is slightly shorter, so this one gets you to coffee faster. Okay, so I will also be way more rabid talking about this one because it was my sworn enemy in grad school. Okay, core halo mass relation. Who wants to hear about it? Let's see hands. There's too many people in the room for me to do this. Okay, supernova. Who wants to hear about supernovae?
Gotta be both.
I don't have time. You want coffee? Ask me a coffee. The core halo mass one. Okay. All right. Frank was on my committee, and he took 2 hours to grill me after I defended my PhD, so I think he's had time to choose what I'm going to talk about. I wore heels. It was a bad idea. My feet hurt. Okay, the core halo mass relation. Okay, so the central question is, if this is my cartoon of a ULDM halo, right, how big is this bump in a center for a halo, right? So I expect this to kind of sort of be related to the mass and size of the actual halo. So the question we are asking is mass of soliton divided by mass of halo equals what percent, right? And so this is an interesting question to ask in terms of understanding the population of ultralight dark matter halos that might exist in the universe in this case, especially since we know, we know that halos are built up hierarchically, or we think they are anyway. But the solitons sort of work differently, which is to say that the more massive a soliton is, the more squelched it gets, which is also incredibly annoying for simulating because you need more and more resolution. And this is a really good question. It was such a good question that there were 3 different answers in the literature when I started thinking about it. So this is the Shui et al. Paper that Chanda mentioned yesterday. So this one is a little bit different than these because these are, slightly more honest-to-goodness cosmological simulations. And these, like all of the simulations that I do, are idealized simulations where halos are built up through mergers of sort of masses simply because we don't have the resolving power to sort of evolve them in a cosmological box. So there's the Schwabe et al. Work that found, some slope, or actually, let me back up. Let's look at the Mox et al. I like this one just because the labels on the axes are the biggest. So what we have on the y, that's not even a joke. What we have on the y-axis here is the mass of the core over the total mass of the halo. So this is the question, what percent of the halo is in the core? And then what we have on the x-axis here is some parameter psi, which is the absolute value of the energy of the halo divided by mass cubed, and then like some numbers that make it unitless. And so this is the parameter that existed in the literature, so this is the parameter that I'll be showing you against as well here. And so Mox et al. Did a bunch of sims with sort of a bunch of solitons initially placed in a box, and then they merged sort of chaotically, and then at the end they measure the mass of the core and the mass of the halo, and they get a slope of like 1/3ish. Schwabe et al. Did binary mergers, so it was always only 2 solitons, and depending on the runs, there's some range here, but about 1/4 is sort of the 1/4 to 1/6 is sort of the quoted number here. So yeah, our question was, okay, given that we have this like interesting way of defining a halo core and like wresting it from the simulation, can we say something interesting? Can we tighten up these core halo mass relation constraints? And so we ran 3 types of simulations that I'll be referring to. So in each of these cases, we're building up a halo, firstly through simultaneous mergers, which is to say that when merging my solitons to make a halo, I force them all to merge at the same time. What this means is that there's no merger history of the halo, right? It hasn't undergone through merges, it's just sort of formed at the same time. We also do sequential mergers where we force these 2 solitons to merge and these 2 solitons to merge before merging the center. So in some sense, this is a halo that has lived through at least one merger event of halo-like objects. And then the mass ratio mergers are the same as simultaneous mergers, but we just vary the masses of the solitons being merged to sort of like kill a little bit of the symmetry. Right. So once this is done, we have some halos. So here I'm showing you data only for the simultaneous mergers. And what I'm asking is what percentage of the mass in my box is just in the ground state, meaning just in the soliton, right? These numbers here tell you how many solitons I'm merging, so a higher number means a higher total mass of the halo because I put more mass in my box. And so just following the n equals 2 case, what we have is nothing because the solitons haven't merged yet, then whoop, suddenly there is a ground state in the core and it's oscillating vaguely around some number. And these oscillations happen because we're in the interaction picture, right? And all of those sort of messy things are happening to the center. It's breathing, it's walking around, stuff like that. So we're just considering the ground state, which when normalized, C0 squared is just MC over MH, which is what we want. Now a note on that, when properly normalized. So we ran we did 2 versions of defining the total mass of the halo, not the mass of the core. First was just how much mass do I put in my box? That is easy, that is a number that I a priori know. However, note that this is not the mass of a halo. This is the mass of a bunch of solitons sitting in a box that haven't formed a halo yet. On the other hand, what we can do is sort of let the halo form, show its average sort of profile, and then integrate that out to the edge of the box and have some average mass of the halo after some time. The reason we want to do that is because I have sponge boundary conditions, so if mass is ejected, it doesn't come back on the other side of my box. So it is always leaking a little bit of mass. And so in this case, I'm specifically not considering these corners where some mass might be hiding, but that's not really part of the structure that I'm interested in. The other thing that we do is we compare fitted and eigencores, meaning do we extract the soliton from our simulation by fitting the profile that we know a soliton must have, or do we use our nice eigenstate approach that we were really hoping would be super, super nice and clean, right? So let's start up here with the black lines. So in both of these cases, what's similar in them is that we are using this version of the mass of the halo. So how much initial mass did I put in my halo? So first, the eigencores are the full line and the full points. And the fitted cores are the sort of empty diamonds and the dot dashed line. And so what we can see is that these don't really differ that much from each other. The fits are, 0.223 and 0.228. I would read both of these as about a quarter, so that's sort of Schwabe et al. Number that they got. And so they're not really that different, right, depending on how I define my, my core. On the other hand, if I look at the purple here and I think about the average mass of a halo, so now this is how we're defining the halo mass. I can again look at the eigencores, which are in full, and the fitted cores, which are empty diamonds, and then dot dash. And again, these don't vary that much, but they do give us different numbers than the other ones. So these are about 0.3, so closer to a third, and these are closer to a quarter. So what this is, what the takeaway here is that the difference between how I define my core is very small. The difference between how I define my halo is very large. So we should think about it where we're defining edges of halos, especially in like a non-expanding background when there's no like rho C, and so no nice standard for defining the mass of a core. So here are all of the results for all 3 different types of runs. So this is for the initial choice of M halo. I will not attempt to convince you that any of these fall on a line. However, when we define sort of the average profile of a halo, what we do see is the simultaneous and sequential mergers both fall on about a third. So these are the mergers without any merger history. But the sequential mergers, where we have a merger history sort of built in, are closer to 0.4. So this is different. And so the merger history does also change the slope that we expect. So the takeaways are, surprisingly, the definition of MC only impacts the scaling relation a little. However, the definition of the halo mass impacts it a lot. So this is something that we need to be thinking about. And in either case, non-trivial merger history matters, which I don't think was as appreciated before around the time where other papers like this came out as well. So this means that we can potentially expect a variety of core to halo ratios in the universe, which of course complicates the situation a little bit. Finally, just to illustrate, this is the percentage of the mass of the halo in the ground state, so in that core. And so what we have here in the orange is a sequential merger, meaning that there's some merger history, and in blue, the simultaneous. So not only do these lines not evolve the same way, they also don't reach the same point. So this is something to really, really be thinking about. All right, so summary and looking forward. ULDM is a dark matter candidate with interesting phenomenology. Individual halos can be decomposed into eigenstates. We use Greidner eigenstates to comment on the relative core halo masses or the effect of supernova blowouts. And some upcoming results that I unfortunately didn't want to share with you today because they're not quite ready, but I'm really hoping to have them by the end of the summer, and I'm super excited for. Considering axiverse with self and interfield interactions, meaning what if more than one axion, and what if it can interact more than gravitationally. So this is, I think, part of what Chanda was hinting about yesterday, which like, should we be depressed? And I think the answer is no. I think it's quite exciting, so stay tuned for cool results. I've stolen whoever was the first to do this. I'm also considering what these JWST observations of sort of early halos have to tell us about ULDM, meaning does that sort of fuzziness of the ULDM that causes dynamical heating, would that potentially push these halos out of our observable band, and can we put constraints on ULDM from that? And so that's with Katie Mack at PI and our summer student Nikki Veyu that actually just sent me a very exciting email today, so that's going well. And then finally, if you want a quick break from dark matter at the dinner or at the reception or something, ask me about using Python to study star charts from tombs in the Valley of the Kings and how to analyze hieroglyphic inscriptions with them. And this is with Sarah Simmons from McMaster, and this should also be published this summer. And finally, this is just something I like to advertise. It's a guide to astrophysics, including sort of like some basics, but also a lot of advice from more than 30 women. My friend Ava Polzin, who's a graduate student at U Chicago, did it. And because fuzzy dark matter is best with a fuzzy friend, this is my cat, Fat George. He's a bastard, and I love him. Thank you.